Hello, good evening. Hi, my name is elajev, and I work for the GraalVM team and at OracleLabs at Oracle, and we're gonna have this session on the GraalVM native images, which is a very exciting part of a very exciting technology. I'm very happy to see all of you here, quite late in the evening. I have a question. How many of you have seen the deep dive, everything you need to know about GraalVM on Monday? Because there was a chapter on native images which heavily uses the same content, right? So also yesterday there was a tools in action section, GraalVM native images explained. How many people of you seen that? Not very many. Very good, because it also will largely go over the same content. So I just wanted to say, if you were present at those sessions, thank you very much, but you might be better at a different session currently. For example, I know in a different room, there was Graham Rosher from Micronaut team is doing a session of GraalVM on the Micronaut native images for the serverless. So you might be interested in attending that one instead. However, there were not many people who did that, so we are ready to start and roll and talk about GraalVM native images in more detail. Before we start, there are some important disclaimers, and before we talk about native images, we should talk about GraalVM in general. It's a large project, it's a versatile project, it can do many things, and in general, it can run your programs in different languages. So GraalVM is a high-performance polyglot virtual machine, embeddable virtual machine, for different languages. GraalVM has two main goals in its advancement. GraalVM wants to run programs more efficiently, to run programs faster, independently from the language, independently from the environment where they're running, to run programs faster anywhere, so to speak, and to make developers more productive by being a unified, single runtime environment that can handle different languages, that has the same operational knowledge necessary for different languages, that is flexible, lightweight, and satisfies a number of requirements that developers want from a runtime. So what GraalVM can do currently? We have support for different languages. We have support for the JVM languages, Java, Scala, Kotlin, Groovy, and so on. Ceylon. How many of you write daily in non-Java JVM languages? Quite a bit. What do you do? Scala? Kotlin? Oh, quite a few. Clojure? It's a very nice Lisp-like language. Groovy? Some people write Gradle scripts for a living. Joke. Groovy is a general-purpose programming language. GraalVM loves all the languages, so there is no need to point fingers. Right, so we also support other dynamic languages like Ruby, JavaScript, Python, R. There are bindings for other languages as well, more interesting. We have support for some native languages that go through LLVM toolchain. Right? If something compiles with LLVM, we can take the intermediate representation of that compilation, and we can run that code on GraalVM. We enable the efficient mixing and matching of different components of your system in those languages, so you don't have to actually have the barriers between different languages. And GraalVM can run programs in those languages in different environments. We can run it on the JVM. We can run it inside a Node application. We can run it embedded in native and Java applications, right? So Oracle has a fairly established and known native application, and you can potentially embed GraalVM in applications like that. And also you can compile some applications ahead of time into the platform binary. It's a native binary specific for your platform that will run without any dependency on the JVM, and potentially without even dependency on the operating system. And this is what we're going to talk about mostly today, about this standalone AUT compilation mode that we call GraalVM native images. In general, you can be interested in different things about GraalVM, and mostly that is the high performance for languages, specifically for the JVM languages, actually for dynamic languages as well. we have this low footprint ahead of time compilation mode, and we have the polyglot things. So today, in this session, we're going to concentrate specifically on technology called GraalVM native images, which enable us the low footprint ahead of time compilation for JVM-based languages. Right? It will give you two main advantages. It will give you instantly fast startup, ridiculously fast startup, milliseconds. And it will give you the runtime characteristics where you can run the resulting programs with much lower memory overhead. Right? So we can run a microservice and make it consume like 15 megabytes of RAM. This is what we're going to talk about. Before, there was a session by Thomas about the performance and the JIT compiler, so you can watch that on YouTube, but that's in the past. And I just wanted to mention that tomorrow, if you're interested in polyglot or embeddability, or if you're interested in GPU, then there is a session by my colleague, actually by two people, about GraalVM and the recent addition to the GraalVM ecosystem, the language GRCUDA, about accessing GPU kernels from any of the supported languages, which is fairly, it's not related to this session, but it's kind of interesting for me myself. And I think anyone who has access to GPU, right, should be interested in that. So you should all go there. Right, but this is in the future, and today we're going to talk about the native images. If you want to get a hold of the GraalVM and try all the demos yourself, or try to run your applications on GraalVM, you should do so, and I would certainly be very happy if you will give it a try. There are two flavors of the binaries that you can get. GraalVM itself is an open source project. You can look at the source code on GitHub. It's written in Java, so most of us could understand the code. Even for the hardest bits, like the compiler, you can certainly open the code, load it in your IDE, and stare at it. I often do, pretending that I understand the details. But yeah, so it's written in Java, it's open source, it's on GitHub, it's with the open source licenses. You can build it yourself if you'd like. And we provide the binaries for that based on the currently JDK 8. And you can download that, and you will get the GraalVM Community Edition. And there is also the GraalVM Enterprise Edition, which is an Oracle product. So potentially you can opt into getting support and whatnot. And it differentiates on the even better performance. And you can get that from the Oracle Technology Network and evaluate that and run your sample applications. Or you can run that on Oracle Cloud for free. So you can get a hold of that. You can try them, definitely. And you can make it work. And they're functionally equivalent in terms that all programs that run on one version would run on the other, on one edition, sorry. Right, so you got a hold of the binary. What you need to think about is that there are two modes of how GraalVM can execute your Java applications. Right, there is an AOT mode and there is a JIT. With a JIT, it's very simple. It's the same Java runtime that we all know and love, right? So you can run graalvm/bin/java, and you will run the JVM. With AOT, is a little bit more. There is one intermediate step. Why would you prefer one to another? Because this is the corner case question of the existence of the GraalVM native image. Why would you like to prefer native image over non-native image, right? It's all about performance. And performance is a lot about different characteristics at runtime, right? When we talk about performance, there are different dimensions how we qualify what is performant or not. And this is a number of things. This could be thought of as a throughput, right? How many requests per second can we handle? Or this could be performance often means to people latency of the serving requests or processing or some computation. Could be startup speed, could be the memory footprint, could be the packaging dimensions. I've also seen an updated version of this diagram where there were more dimensions like monitoring and some others. Don't remember. There were more. But what I want to say is that there are different things that we mean when we talk about performance, right? And we have in mind a trade-off that when we run with the JIT has very good view into the into the runtime characteristics of your application, right? It knows the code that it runs, it knows the data structures, it knows which code paths are hot or which code paths are less important to be exquisitely optimized. It knows what data flows through it, right? It knows data types, it knows the amount of data, it knows the approximate lengths of the arrays that you're passing to methods, and so on. JIT has the best visibility into the system because it has that information at runtime. So it can optimize the code to the best, and it also can speculate and then de-optimize. This is what the JIT does, right? It makes a guess that, oh, I think only integers will go through this method. And it generates the code to handle it very efficiently. And then when a string comes in, or I don't know, a Java object, right? Then it de-optimizes and revisits its assumptions and does its job again. So it can be speculative, and it can be the most aggressive with optimizations. So it probably will be the best, some sort of JIT, for the peak throughput. And most probably for the latency as well, because that is the inverse of the throughput. However, running with a JIT requires you to warm up the application, right? The system needs to gather the information about your application to make those decisions. You need to warm up your application. It doesn't start really, really fast from the get-go, right? It needs some time to understand what code is running, and so on. So an ahead-of-time compiled application will probably beat the JIT version on the startup speed. It cannot include the facilities for JIT compilation, so it cannot consume memory for that, right? Imagine if you need to compile Java code, right? You would probably need some intermediate representation, maybe a graph, and you need to hold that graph in memory to compile and modify that, and that will take memory. Duh. So if you don't have to compile, you don't have to allocate that memory, and you can run with a much smaller footprint. You might not need to store bytecode at all, right? If you compile everything ahead of time, no bytecode, no memory consumption for bytecode. Maybe some metadata about the class files, maybe some reflection configurations. You can save some operational memory on that. So you can run in a much more constrained environments. Luckily, this trade-off is not the direct obstacle to GraalVM, because GraalVM supports both of those modes of running applications. You can run your applications on the JVM with the JIT, and you can compile your application using the native image utility, thus the name native image. And you feed your application, your jar files, your classes, to that utility, and it computes it for some time, various amounts of time. The fastest I've seen was 6 seconds, just earlier. And then it provides you with a binary, and you double-click on that binary, and it runs, right? And I'm going to show you a demo, and there are a number of applications that I can show you that are compiled as native images, but I would like to show the most appropriate one. So it will be a web service, and it will be written using a framework for web applications. How many of you use Micronaut for web applications? Just a few people, not bad. How many of you use Quarkus for your web applications? Quarkus, just the session before that, they just announced 1.0. Congratulations, Quarkus team, on the release. Right? How many of you use Spring framework? Spring Boot included? Right? Plenty. I assume that others are just writing open source libraries. Or something else. Desktop applications? A few. Unfortunately, I currently cannot show you a demo of a desktop application, like with UI and everything. But stay tuned. Very soon, I've heard things that we're going to show that. So since most of you use Spring, I'm going to show you an application, the demo application of the Spring microservice compiled as a native image. Yay, go Spring. And of course, I wouldn't be able to do that just by my efforts. And I had help from Sebastian, who did a session on Spring and native images just earlier today. And I felt that was a wonderful session. So I recommend you watching that. And he gave me the instructions how to get the demo applications working. So it's a work in progress. GraalVM team and Pivotal engineers, we work together on making the Spring support native images better, and native images support Spring framework better. And there is progress being made. And I'm very happy that today, currently, I can show you this application going on right now. So what do I have here? I have a pet clinic application. Pet clinic is the most known demo application. Oh, sorry, something is happening. This is just my Mac. Not the most powerful Mac in existence, so you have to understand that. But a pet clinic application, and I have the source code for you as well. Literally, this is the normal pet clinic Spring Boot application. And you can see here in this folder, let me just show you for you, right? It's the Spring Graal native samples, Spring Pet Clinic JPA. So it's a Spring Boot Pet Clinic application that uses database through JPA, right? It's a complex microservice. This is what many people write for a living. Small microservices that access the database, send a few messages to Kafka, render some JSON or HTML, right? Who recognizes that description for what they do? Who does microservices? Yay! Go microservices. Next time I'm going to show you a demo with Kubernetes, so you can efficiently deploy your microservices more efficiently. However, I digress. I have compiled my native application as a native image into this pet clinic, and this is not optimized, right? This is just the beginning of the support, and it's a work in progress, so there are a few rough edges, and we're working forward. However, this is a binary, and I can do tool, I think -L. Was it -L? Pet clinic, and you can see that this is a binary, and it links directly to the operating system libraries, right? There is no dependency on the JVM. It's file pet clinic. It's a binary file. It's an executable binary file, and it's called pet clinic. So we're gonna run it, and it's gonna hopefully give us the pet clinic application. Boom. We'll run it again to warm up the caches for the machine, and it runs and it starts in 0.3 seconds, which is not the greatest result on my machine. 0.12 seconds. This is much better, right? So this is not the best result. I can show you that actually it works. Look, it's a complex pet clinic application. How many of you have seen pet clinic applications? Right. So this is the application that is the clinic for imaginary pets. And it uses JPA, and it uses some query, and it queries some database. Currently it's in memory, and it works. And it displays you some data, and you understand what technology is behind, right? There is database driver, there is sending marshalling objects, there is JPA, all that, and it all works, and it starts in ridiculously small amount of time. Besides starting in a small amount of time, I can do this following thing here. I will show it to you. I will figure out the startup, and I will plot the resources usage for this particular application. Using the utility called, this. I will use the utility called PS record, and I will plot how much CPU time and how much memory it consumes when I run it. I'm going to start it up, and I'm going to send 3 requests to the URL that fetches things, right? Let me just kill it, and we will do plot, and we're gonna do pet clinic, and we're gonna do pet clinic. We're gonna go into details more about that. So it starts, it does 1 request, 2 requests, 3 requests, and it gives me the plot. And here it is. What you can see that the memory consumption grows on every request, but this is not what's important here. It could not grow as much. We can limit it. It has access to a lot of memory, so it consumes a lot of memory. What you can see is the red bumps here. The red means CPU usage. This application, when I start, does work only when it actually has to do work. So we start the application, and it does nothing. There is no red over there in the left corner. In the left corner. Yes. And there is only work when we send the request, which means this is a very efficient way to deploy your applications. right? This is very exciting. I just saw this demo just before, and I'm very excited that I can show it to you. Let's go back and let's go into some details about the native image, what they do, how they work, and what you should know about them. Besides that, there are some initial progress about the Spring applications. How many of you are excited about the native images for Spring applications? Nice. How many of you are excited because of the startup gains? Approximately half. How many of you for the memory consumption here? Almost a half. So it's half and half. How many of you don't care about startup or memory consumption? One person. All about JIT. Very good. Or maybe a Golang developer. Sorry. All languages. Love all languages. Right. So what happens when we build the native image? What happens when we build the native image is that all the classes of our application are analyzed. The native image utility gets a hold of you feed your jar files to it, right? So it takes your application classes, your dependencies, like the Spring Framework and the JPA and the driver and what else? The dependency injection mechanism and the REST API and the annotations and Kafka streams, drivers and whatnot. Everything besides Maven, Gradle and other build tools. The whole thing is taken into account. It takes into account the JDK class library, because there are also classes, and it takes into account the classes that implement the bits for the runtime system, like GC, or like the thread management, right? Because your application would like to have those abstractions when it runs, and it doesn't matter whether it runs in ahead of time compiled mode or in a JIT, right? It still would operate under the assumption that memory is infinite, because that's how we write programs. Because we are in a managed environment where there is a GC that actually makes it true. So the native image has to run with some sort of GC as well. So that GC implementation comes from the project under GraalVM. So all that is written in Java, so it all can be processed in the same way. So we analyze that, we initialize the application, which means we look at the classes, we initialize the classes, and when we snapshot the initialized heap and write data and the compiled code into the final image, we wrap that into the linked ELF format binary for the operating system to know how to execute this, and voila, it's done. A more detailed view for the analysis is that we load the classes, we initialize the classes, we figure out which classes reference other classes, right? This way we load all the classes that will ever be executed, like everything that points to something, we load that. If something points to the class that is not present, who thinks it will, nobody, I don't know whether you think, it will output an error, right? If class is not present, we would like to see that. You have to show us the class. We'd like to see the bytecodes. So we do the point to analysis and we run the initialization for the classes, which is very important, and then we snapshot the heap, as I said. So literally taking the objects on the heap that are left there after you initialize your classes, after we run static initializers, and we write those objects into the binary. So that's what you get. In a native executable, you get the code compiled ahead of time by the GraalVM compiler. It's the same compiler that we use in the JIT mode, but just used differently. If you will, when you have a JIT compiler, it takes bytecode, it takes the profile, and it outputs the machine code, right? So when you want to use a JIT compiler in an ahead of time compiler mode, you give it the bytecode, you give it null, and you output the machine code. There are differences, of course, in how it processes the bytecode with and without the profile and the specific optimizations, but on the signature level, on the API level, this is fairly clear, right? You just give it a null. Probably not the best practice, but a good illustration. So, and then it outputs the machine code, and then it outputs the heap. And the most important thing to know about this is that the whole thing operates under a closed world assumption. It means that the native image utility has to see all the bytecodes that will ever be executed. There is, you cannot, after the native image is generated, you cannot add additional classes because they consist of additional bytecodes. And native image has to see all the bytecodes. So there is no new loading classes at runtime. And also there is certain complications, but moderate complications, like minor inconveniences rather than actual problems, with some dynamic parts of your programs. If you use reflection, for example, the static analysis cannot just figure it out, right? It's just impossible, because the reflection usage can be constructed at runtime dynamically. So there is no possible way for at the generation time, statically, without executing code, to figure out the reflection usage. Or proxies, or some other things. So, but the closed world assumption is not there just for fun, because someone thought, like, I should make engineers struggle with providing me additional configuration. It's there because it allows the AOT compiler to make more aggressive optimizations and output better code for a number of reasons. And otherwise, if there is no closed world assumption, you need to provide the machinery for dealing with bytecode. Right? If you allow bytecode to be loaded and compiled and treated at runtime, you need the facilities. And you need to bring those facilities with you. And that means that you will need to have the overhead. You will pay in the memory overhead for those facilities in the JVM, for those components. Because you will get the bytecode and you need to compile that. For that, you need the compiler. For that, you need to allocate memory, and so on. So closed world assumption, very necessary. Very necessary. Right. But what it allows us to do, it allows us to instantiate classes and instantiate objects and write objects into the image heap. Right? Because we've seen all the classes, we know all the initialization that has been done. We can literally snapshot the execution of your application at a certain point. After some work has been done. So for example, the class objects and the enum constants, they could be literally initialized once and then written out as objects. So when you start your application, you don't have to do additional work. Think of this way. If you conventionally compile your sources, your Java C compiler compiles Java code to Java JVM bytecode. And then when you run it, the blue things, you load the classes, you load the configuration files, you verify everything, and then you compile those, and then you run the workload. With the native image, you can move that limit, that border between the build time, between the native image generation time, and the runtime to a different level. So for example, you can load the classes and store the classes. And since we know that there will be no other classes, because of the closed world assumption, we can safely do that. So you don't have to do that at runtime. Which means what? Which means faster startup. Doing less work at runtime, especially in the beginning of the runtime, means faster startup. Because not doing unnecessary work means you're faster to get the actually useful work. Unnecessary in terms of the workload, not unnecessary in terms of like unnecessary bad, right? And you can also do it further. You can load your configuration files, and if you are careful about how you structure your code and how you write and use the native image utility, you can do quite a bit of work and prepare your application and prepare some data structures and use them already ready for you in the generated native image, right? So when you start that, you don't have to initialize anything. You don't have to initialize locals or calendars or simple date formats that you're gonna use or stuff like that, utility things, right? You might configure that at the build time. And then you just run your workload, which gives you really, really good startup. Right. So what else? Inborn embeds, dynamic features, which cannot be figured out statically, right? For example, reflection. Some people tell me that reflection doesn't work on GraalVM, that GraalVM doesn't support reflection. I hope none of you will be such people, because GraalVM supports reflection very well. For two reasons. First, GraalVM can run your applications in the normal JIT mode with a GraalVM bin Java. Duh. And the second part is it just requires a little bit configuration. The configuration could be in different forms. It could be, actually it's in most common form for the reflection specifically, is the JSON file that says, I'm going to touch this class and I'm going to run this method reflectively. And I'm going to show you a quick demo for this. A very quick demo for this. Right. I'm going to show you this very quick demo for this. Right. I have the file here called hello reflection Java. Right. A very simple Java application. It just takes the arguments and runs reflectively the one of the two methods that it has. So when I do Java, I compiled this. I think I will compile this again. Right. We Java C hello reflection Java. Right, we got the bytecode, and now what we can do Java hello reflection, and we can do foo, and we can do devox. And then foo devox, foo Oleg. Right? And then we run one method, and then we say that there is no other method. Right? If I would build a native image out of this, by default, it will not handle the reflection well. So I will need to provide the configuration for that. So the configuration looks like this. Let me show you how it looks. It looks like this reflection file, this JSON file. I will say that my hello reflection class will have to expose method called foo with no parameters for reflection usage. If you're wondering how I generated this file, how I got this file, I could write it by hand because I'm a capable developer with hands. I get paid for typing correct things into the computer. Also sometimes talking to people about how I type things, but I digress, right? So another thing is I can generate this. There is a Java agent that you can run, and you run your application in within a normal Java process with that Java agent, and it will record all the access to reflection, proxies, and everything else that requires configuration, and it will output the configuration for that. Check this out. So run Java tracing. I just use the native image agent, and I configure where to output configuration. Right? And I will, just for you, remove -ref metadata, no / in the beginning. So there is no metadata anymore. And I will just run Java tracing. And you can see that I run it in normal Java, and I give foo and xyz. And I'm running foo, and I'm running no such method exception. And my reflection now, my reflection configuration is back to being foo. So this agent records and provides configuration for you. So you don't have to do that manually. You can extend it manually, right, if you want to, or you can look at it and change it because it's human readable, but you don't have to actually start doing that by hand. And that simplifies configuration for the native images significantly. And now what I can do, I can compile the native image, and I think I compiled it before, and I can do hello foo, and it will run foo. Because now, even though this foo method is accessed reflectively, now, while I generated this image, there was configuration that says this has to be included. Native image complies and includes that. And now we can run this. The same with the proxies and GNI and so on. Magnificent, right? Tooling to the help, which is very good, very good. So reflection is not a problem. Reflection has very good support in GraalVM. Another issue that you might be wondering about related to the closed world assumption is how do you deal with the incomplete class pass? Right? Very often you can be, there is an idiom in the Java code, which we all use and love, right? The same way as with reflection, right? Everyone uses reflection. It's a good feature. It requires a little bit of configuration for the native image. The class pass. You check for the class existence on the class pass, and then you do something with that information. If you have a Neo4j driver on your class pass, maybe you want to configure a Neo4j access bean in your application, right? Or if you have a certain logging framework on your class pass, maybe you wouldn't like to use that automatically, right? So if you don't use that class, if there is no class on the class pass, you don't do anything. You just don't load it and you don't run with it. With native image, that doesn't fly. If there is no class that someone is references, then there will be no option to link that class later, because no additional class loading, right? Of the closed world assumption. Right? So what you need to do, you need to provide old bytecodes. And if a class is missing, boom, done. There will be an error. Native image is very smart, and it doesn't allow you to do make mistakes easily. So what you can do, you can add the line option, allow incomplete class pass. And by that, you say that when you see a class that we would like to use, but it's missing, don't freak out. This is normal. I know that my application sometimes references Groovy. Doesn't mean that I actually use Groovy at runtime. It's just there through the transitive dependencies. Sometimes. Sometimes not. So this will defer throwing errors to the runtime, because we allow the incomplete class pass. Another thing that we can defer to runtime is the class initialization. So I said that we can control when we initialize classes. Right? Sometimes we can initialize them at build time, and we do that for the JDK classes by default. We know them, we've seen them, and we can initialize them during the native image build time. And classes of your applications are by default deferred with the initialization until runtime. What you can do as an optimization, you can say, I know that what I'm doing, and I would like my class and my application and my framework to be initialized at build time. That will help tremendously with a startup, because not tremendously, it's not such a big cost for the runtime to initialize those at runtime, but it's still an optimization, and you can do that. And specifically, you can do that if you do some things at startup which you don't actually do at runtime. For example, you are parsing an XML configuration file. Sometimes you configure things with XML, and for that you need to load the features and the facilities to read and deal with XML files, right? But then maybe your application never deals with XML files after all. Right? Maybe it's not in this business functionality requirements to deal with XML files. So what you can do, you can initialize at build time, do things, and then never think about XMLs at runtime. Right, so class initialization. It could be a little bit challenging, because the chains of class initializers could be unpredictable, because some classes initialize other classes and then initialize further classes, and you end up with within AWT class with trying to start a thread. And this is a no-no, because you don't want to start a new thread during the native image generation, because that thread cannot survive till the actual runtime. So there will be an error. And to help with those class initialization chains, there is an option called trace class initialization. You can put it in, and the code will be instrumented, so when the classes are initialized, the stack traces which initialize the switch will be recorded. So when you encounter an error, you can see how exactly you end up there, and you can do something about that, which is very good, very good. So another dynamic feature, which is luckily doesn't require any configuration, is a service loader. Right? You can provide some classes implementing interfaces, and then it uses a combination of resources and reflection to instantiate and use the classes for the interfaces without like a direct requirement and connection on the class. So the native image does and understands the metadata and does that automatically. So some things are fairly automatic with the native image. Right, and at the end, if everything else fails for you, and you specifically want to run your application on the native image, you can always do so by using a lower level API. You can determine, there is an API to figure out whether you're running during the generation of the native image, at runtime of the native image, or you're running on the in the JVM process with a JIT. This means that you can shape your code to make the best usage of the features for the native image. I'm not saying that you should do that. I'm saying that you can. Because as developers, you have the ultimate power over the application that you're developing. No one else knows it better, and no one else can change it as well as you do, hopefully. Right. So you can figure out, there are other mechanisms how to make it even more configurable and what you can do. But that is more of a topic for the deep dives and so on. or tutorials rather than a session, because you would like to try it to learn the best. Right. You can embed your configuration into the libraries. There are a few things. You can configure that from runtime from the command line, saying that native image initialize at build time this package, or initialize at runtime that class. You can put that into the meta-inf directory, meta-inf native image, and you can put that in a jar file. So if you're doing a library, if you're making a library, if you're distributing your jar files, you can include the native image configuration that will simplify the usage of native image by your users. One project that does that is Netty, as a server. And we are very happy to see that. Right. Additional thing that you can do with native image, you can include the profile at the time of generating native image. And it is a GraalVM Enterprise Edition feature. You can run your application on the JVM, and you can gather the profile and see what code is actually executed. And you can use that profile information while you're generating a native image, and it will be faster because it will use the profile. Very well. And then we go to a demo, and I'm going to show you a little bit more of the applications. So we looked at the Spring pet cleaning, right, and some reflection. Let's look at the other application. Let's look at the Micronaut example. Wait, let me show you. LL. This is the Micronaut application, and this is a very simple application. Sorry. This is my PowerPoint skills. See, even though my official title is developer advocate, I think there's something from a developer in me. Right, so it's a simple application. Let me just show you. I will run it. The best way to quickly run your application is, of course, on the GraalVM native image. Right, it starts up in 21 milliseconds, and it's a simple. Oh no! This is a different. This is an application that does quotes. Right, shows you quotes, random quotes. From some people, and I took those quotes from that GitHub repository with a permissive license that you briefly saw in the browser. Right, so it's a very simple application. Right, it literally does nothing but queries a service. There is a controller. It maps to a service. Service gets random quote. The quote gets returned, marshaled into JSON. Not so simple, actually. It's quite a heavy machinery involved. But in a use case, it's fairly simple, right? And we're gonna make this application our pet, our experimental pet for the clinic. What I want to show you is that I'm running this application, right? And if I look at the memory consumption for this app, right, my quotes app, it's 17 megabytes. This application, this microservice that outputs very wise inspirational quotes, consumes 17 megabytes at runtime. Ta-da! It deserves a route of applause, but I understand that not always we are very good with excitement, right? So what is interesting here is if we look at this quotes app, it's larger on disk than it is at runtime. Personally, I have no explanation for this. I know that other people smarter than me do. Some of them you can find at the Oracle booth at the expo when you come and talk about amazing information you learned about GraalVM native images at a session in the evening of Wednesday. Right, so it's an application. I can also run it in the Java mode. Look, I have a file here, run, right? It runs my Java, no? What's this? But run. No, this is different. This is right. We run this application as a jar file, right? Let me run this. It's an application. I run it with my Java. It's in normal Java, and it starts up really fast, fairly fast, in like a second and a bit, which is very fast. It's really good, right? How many of you can say that your application starts up in a second? 2 seconds? 5 seconds? 10 seconds? Good. Half a minute? Somebody uses WebSphere? Or any other large application server. They all have similar runtime characteristics sometimes. So 10 seconds was, I think, which got the best response, which is very good, very good. I hope you write some microservices. What is more important is there is another metric that I want to point your attention to. Startup, until we see a log line that my startup is completed in X milliseconds, is not actually starting up. It's just getting to the point where you're like, yeah, I'm doing work. Sometimes people come to you and ask, like, are you ready to give me that report about the DevOps? And you're like, yeah, of course, I'm ready. I'm ready. And then you start typing. Right? So the question is, when you actually are ready to do meaningful work versus when you are just saying that you're ready. And to do so, I have this small script here. And I will show it to you. It's called startup test. What it does, it starts the application that I will pass it. And it will curl it. And until it gets the 200, HTTP 200, until it gets HTTP OK, it just sleeps 20 milliseconds and curls it again, right? We start the application and we start pinging it. And then we measure time, the CPU time, not even the wall clock time, the CPU time, how much it took until we exit this while loop, right? So we ping the application until we get the response, and then we kill everything and print how much time it took. I mean, we measure the time first, and then we kill everything, right? So this is the time until the first successful response, right? Which is actually startup. Let's see. If I do, what was my command there? Here, I will copy this, right? I will do this. And my Java, if you're wondering, which Java, this is actually the GraalVM Java. Why is this? This is Java. Okay, it's a GraalVM Java. Right? It's a Java inside the GraalVM distribution. You will see that we'll have the Java 11 based builds very soon. Currently it's Java 8, but soon we'll have Java 11. What I was doing startup. I was doing startup, and sorry about this. Where's my Java command here? Jar. Right? I will do startup test, and I will do this, and I will say it's a jar, and I will start it. So it starts, and we ping it, and in 3 seconds, in almost 4 seconds, we got the first response, and we kill everything, right? I mean, we got response, we measured time, and we stop it. And it could be better. It could be better. It could be better if you use more powerful hardware. I think it converges to this number on my machine. So this is a startup. This is the almost 4 seconds of CPU time until we get the response, right? With 20 milliseconds increments. Plus minus hardware, plus minus turbo boost and all other questions you have to this, the most scientific benchmarking environment in existence of humanity, my MacBook. Right, so I digress again. What we will do the quotes up here, and we'll do the same test, and it's 40 milliseconds. To serve the request. And I can show you the plot test for the Java, because this is very interesting, right? The plot test was doing 3 requests, right? And showing the CPU. You can see some Java is in many ways C++, unknown. And the graph for the CPU usage is different, right? At the startup, we do a lot of things. We initialize the JVM, we load the classes, we verify the classes, we start compiling some code in those classes. We do a lot of work. And also you can see the memory consumption is like 400 megabytes for 3 requests. I mean, I could probably limit it, right, with configuration. But like 400, this is still like quite a bit. Quite a bit of that chunk is actually the overhead for the JIT facilities and the compilation facilities, whatnot. So if I do plot test quotes, quotes up, the image is significantly different. It's very similar to the image that you saw about the Spring application, right? Work only when the work has to be done. Very efficient. and 35 megabytes of RAM for a few requests. If you're doing serverless, or if you're doing like function as a service or microservices, this is excellent. There is a question.
Can you further limit the RAM, maybe with an XMX option?
Yes, I can. That's a good question. You get a pair of socks, Thomas. I can further limit the RAM with the XMX option, and I will do 16 megabytes. And I can do the same thing. And there are some quotes about failure. This gives me like a stresses me out. Not so much, for some reason. I think something was wrong with this. But we limit the memory. Actually, we can limit the memory. One other thing that we can limit is, I think, the young generation of the thing. We can try the young generation where objects are located, and until we fill the young generation, there are no garbage collection. X megabytes, no test like production. Right? And then, yeah, it's still the same. I can show you a better version of this later. Currently, we are running out of time severely, so we're going to speed up with our takeaways because we're out of time. There are ways to jumpstart your project. There are some options. You should use them if you know and understand what they're doing. There also, you can use one of the frameworks that declares their compatibility with native images. For example, Halidon or Micronaut, or recently Quarkus released 1.0. And you get both startup and memory improvements from using native images like no other technology gives you. Right? So normally you would run it and it will be like much slower startup, like 50x, and something like 5 times more memory consumption. We will improve the other performance characteristics of the native image. And what you should take away from this session is that you should be interested in this technology and keep an eye on it. And that you can use GraalVM both for your normal, typical Java workloads and native image workloads. And you should talk to us. You should ping us. You should read the docs. And most importantly, you should download it, try it. Thank you very much.